So today I'll be discussing the coin tossing problem that I've been mentioning. I call this coin tossing with Uncle Bert. And Bert, of course, refers to Bert Capon, the uncle of this particular problem. It's in reference to this family friend who would always give us $1 if we would do or guess certain things. So this is reminding him of my parents' friend Ronnie, who called himself Uncle Ronnie. And, you know, when you're doing a control problem with a similar kind of setup, I think of Bert Capon as kind of giving me $1 or not, depending on whether or not I get the problem right, because he's kind of reminds me of an affable uncle, even though he's not my uncle either. Okay, so the idea here is that we have two coins. Coin A, which I'll try and keep in red, but I probably won't succeed. And we have coin A can either result in a heads. If we pick coin A, we can either get a heads, which I'll call H hat. It's the outcome of A becoming heads, and we can also get a tails. So these are kind of two possible observations we can see if we take the action to choose coin A. And likewise for coin B. We have these two possible outcomes. And the probability for one or the other is given by it's a coins, right? So it's a Bernoulli trial each time. So this probability of heads here is QA, and this is 1 minus QA. So there's this parameter unknown to us initially that determines the probability of a particular action yielding a success. Right, and it's a success because if we get a heads of any kind, then Uncle Bert will give us $1. Right, so we're trying to optimize the number of successes we get. We have these two coins. We don't know the probabilities, but as we proceed, we see, okay, actually this coin is really coming up heads a lot. The other coin is always giving us tails, so we know which coin to pick. Right, so that's kind of the background, and it'll be convenient to define a prior distribution for coin A and coin B that is beta distributed. So this is QA, and this is var pi on QA. It's beta distributed, so it looks with parameters less than. I mean, it's just traditional to make this thing choose our initial parameters to be 1/2 and 1/2. It's the Jeffreys prior. Talk a little bit about that, right? So QA is equal to QA to the alpha, 1 minus QA to the beta, all over the beta function, alpha beta. I'll give these little, I can't fit subscripts, and I'll give them superscripts as well to indicate that they're the kind of parameters of the distribution for coin A's state. And traditionally, at time 0, the Jeffreys prior is the case where alpha A equals alpha B, or beta A equals 1/2. Oh, these have -1s up here. Right, so that's why there's these spikes here, because they're actually poles. They don't reach 1, but they don't have actually any mass at 0 and 1, but they are poles of the distribution in the sense that the power is less than 0. So this is called the Jeffreys prior, and it's called the Jeffreys prior. What the Jeffreys prior is it's a statement that you choose your prior based on based on making the likelihood flat with respect to a particular choice of coordinate system. So this is really a uniform prior, but where our coordinate system is chosen such that the Fisher information, so the Fisher information is it's equal to the second derivative of the likelihood. The Fisher information is equal to 1. So you right, the Fisher information is a second rank tensor, and so you can it's a second rank tensor, so you can kind of change its value by changing your coordinate system. It gets factors of the Jacobian. You choose a coordinate system that makes your Fisher information equal to 1, and that's kind of the Jeffreys prior. But it's not necessary. The important thing is just that we have a beta distribution. So we believe the coins Uncle Bert tends to give us tend to have probabilities that obey this particular law. And likewise, we also imagine that for coin B, we also have alpha B equals beta B equals 1/2 initially. So now, so now we have to decide, we have to right? So as we discussed, our state is really our belief about the system, right? And the system is really, there's really no, because it's a binomial or Bernoulli trial, right? Each trial is independent, so the state is really entirely defined by the parameters. So that just means that x of t is equal to the posterior distribution on these two parameters, q a and qb, given observations that is heads and tails outcomes we've seen at times less than t. Right, and so what happens when we make an observation? Well, an observation is an outcome, heads or tails. So O is an element from the set. Either you have heads on coin A, tails on coin A, or you have heads on coin B and tails on coin B. So that's the kind of set of all possible outcomes. And what happens when we see an observation to our posterior? Well, because we've chosen our prior to be beta distributed, we have this nice property that the beta distribution is what's called conjugate to the binomial and Bernoulli data. So that means that if you observe binomial and Bernoulli data that have parameters governed by a beta distribution, the posterior distribution is then also beta distributed. So it's sort of like an eigenvector for a particular observation process, except it's not really a vector. It's more of a functional family that's preserved as you take more observations. So let's just see that that's true, right? The likelihood for a particular, for our QA and QB, given an observation, is it's equal to just basically Q U. It's just equal to QU if you see if O equals HU, right? So if you see a heads, your likelihood is just QU, and if you see a tails, your likelihood is just 1 minus QU. So, and this is just, of course, the Bernoulli trial probability distribution. I guess it's easier maybe to think about this as not a likelihood, but just a probability, right? The probability of an outcome given these Qs, right, is more or less equal to the likelihood. I mean, yeah, I don't know. I use these things interchangeably, so it's convenient to write this as a function of the parameters, but it's equivalently also can be viewed as a function of the data. All right, so yeah, and so now you can see, right, if you take your beta distribution for right, so if you take your posterior at time t, this is just equal to the posterior at, well, let's ignore the normalization. Well, okay, it's fine. Let's keep the normalization. So this is just equal to the posterior at time t minus 1 times the likelihood divided by the normalization factor, which is often written z of the observations. Yeah, so if we take this beta distribution, right, so this var pi of QA and QB, these are independent of each other. So it's really var pi of QA, var pi QB. And if we just look at one of these guys, let's look at coin A, and we see that coin A has achieved a heads, right? Then basically this thing is, QA times raised to the alpha A, Q1 minus QA raised to the beta A over beta alpha A, beta A. And then this gets multiplied by the likelihood, which was an observation of QA, which of course was just QA, an observation of heads. And then, so this means that just, if we view this as acting on the parameters, alpha A goes to alpha A plus 1, right? You just increase this power by 1. And then the normalization factor is kind of gets taken care of. You also increment the beta function by 1. And if heads is seen, and likewise, if tails is seen. And so in this special case of a conjugate prior, we actually can represent our knowledge with just the parameters of the parametric family that describes our knowledge. So in this case, the parameters of our parametric family are these alphas and betas. And we have a clear understanding of how these things are going to evolve in time. So we can actually represent our state, right? It's this collection. It's representable as this vector of alpha A, alpha B, beta B. Oops. I was just thinking that alpha and beta and A and B are, of course, cognitively linked and prone to interchanging. So, right, so X can be represented, our knowledge state can be represented as the parameters of this beta distribution, because no matter what we see, we always end up with a beta distribution afterwards. And this is a special feature of the conjugate prior we have and the kind of updates we have. In general, right, if our prior distribution had been something weird, here's 0, here's 1, and it had been a bunch of wiggles, then, and then you see a heads, right, you overlay, oops, it's not, you see a heads, which is just this kind of linear function, q, or 1 minus, you see a tails, 1 minus q, right? This linear function, or this kind of simple function times this complicated function is just another complicated function that we can't necessarily represent with a finite number of bits, right? It's a continuous function on this real line. So, or discontinuous even. It's a distribution on this line 0 to 1. So it's only with this, this conjugate prior here, where you have this nice rule that we start out with something smooth, and then if we see something like this, that just kind of shifts our distribution to something, to something like this, I guess. It moves the mass around, and then if we see a heads, right, we end up with something kind of more familiar and bell-shaped. And this kind of, no matter what we see, we always end up with something that is unimodal and has a smooth likelihood. Right, so we're almost ready to actually define our propagator on our knowledge state. As we've seen, our knowledge state just evolves according to these integral transitions on these parameters, alpha and beta, depending on whether or not we see a heads or tails on the coin we've chosen. So if we knew the parameters, we could already write down the propagator. So the propagator for x, for a given coin, u, where u is an element of A and B. Right, the probability of seeing state x of t plus 1 given state x of t is given by, okay, and also if we knew the parameters, is given by, so I'll introduce some notation here. So first we have the probability of q, the probability of a heads, times this function, which is 0 or 1. It's basically a Kronecker delta. It's called an Iverson bracket. So if the difference between these two vectors is equal to heads, whoops, accidentally created a perfect line. Right, so this heads u is a one-hot encoding. So for instance, HA is equal to 1, 0, 0, 0 for this 4 vector of alphas and betas. And we'll also define, for instance, TB right, and alpha and beta are, and this thing is the, and there's these other things. And we have the other alternative, that the coin we chose turned up a tails. That occurs with probability 1 minus QU. And just in case you're not familiar, this thing here of a statement, this is equal to 1 if true, and 0 if false. I saw this in Donald Knuth's book, Concrete Mathematics, and I found it to be just extraordinarily useful. So really cool notation. It's called the Iverson bracket, named after Kenneth Iverson, the creator of APL, a programming language. So anyway, just fun. If you're a notation aficionado like I am, then you'll probably end up using this a lot. Okay, but as we've seen, we don't actually know these parameters Q, A, and QB. We only have a knowledge state for them. So actually, we need to develop the true propagator, or the complete propagator, I guess. And this thing is just, it can be shown, I'm not going to show it here, that this thing is just the average over the parameter values. Given our current knowledge state of the kind of auxiliary propagator that relies on the incomplete information and the information we don't have. And yeah, this corresponds to, I don't know if you remember the first lecture, but choosing one of these points, right? So choosing a theta at random and using that to move our system forward in time. And the average over all possible choices of theta is this total observation update. So we have in the beta distribution case, right? So if you look at our propagator as it's written, these parameters q and 1 minus qu just appear directly, and so that means we just need to replace them with their averages, right? So this is equal to the average of q u times this Iverson bracket. Right, and these averages can be taken analytically. So we have in our case that the beta distribution, if we have the beta distribution q times, so yeah, q to the alpha minus 1. I'm not sure I always remember these minus 1s. Beta minus 1 over alpha beta. If we take the average of q, this just becomes the ratio of two beta functions, right? So the beta function is sort of defined by this integral, and so this just becomes beta alpha plus 1 and beta. And these have a nice recursion relationship, which I don't exactly remember, but the result is very easy to remember. Actually, you could probably use this result to remember the recursion relation. The result is that the average of q is just given by a alpha over alpha plus beta. Right, so basically, alpha and beta count the number of heads and tails we've seen, and after we've updated our distribution, the average number of heads over the total number of tosses we've seen is roughly our average probability, our expected probability of that particular coin. So it makes sense intuitively, and it's a really just nice feature of the beta distribution. So now when we plug that in, right, we see that we actually have a complete expression for k that just depends on our states. So we don't have any reference now to these hidden parameters. It's equal to alpha u over alpha u beta u. I'll just finish this out. Okay, so we've taken, via this average procedure, we've taken this learning problem And we've turned it now into a really kind of a straightforward Markovian problem where our states are just these states that parameterize our states about our knowledge, right? So X is, again, just this 4-vector of alphas and betas that tell us, that describe the distribution of our belief about the 2 coins that our uncle has given us. So now if we define a cost function, like for instance, that on our transitions between states, such that, we're trying to avoid tails. We just accumulate the cost 1 every time we see a tail. So this is just xt plus 1, x of t equals tails. So yeah, the Iverson bracket also shows up in our definition of cost. So that's nice. So now let's discuss how to generate our cost to go. So it's just this standard procedure, right? Our cost of, there's nothing mysterious now about our learning problem. Our cost at j of x of t to go is equal to the expected. So forgetting our the KL divergence problem, let's just assume there's no cost in choosing coin A or coin B and that we can do so deterministically. This is just given by the minimum of our actions or in this case our actions are our controls of the expected change in our cost. So if we take a particular action, then our cost is expected to change by the cost we see. Our cost to go given a particular action is the cost that we get transitioning to the next state plus the cost to go at that next state. So, and then we're basically done. So we have the terminal condition that j is equal to, if we're at our final time, which I'll call curly t, our cost to go is 0. So we're just counting our cost as we're going along, how many heads and tails we've seen. And Uncle Bert won't deduct us any points at the end or anything like that. So at the end, we've already counted everything and there's no extra terminal cost. So say if the game lasts 20 rounds, then we can start with our, there's lots of different outcomes. We could have seen a lot of different heads or tails, right? But for at every one of these points, we know that our cost to go at j is 0. And then we just have to consider, okay, what's the probability at these nearby states that we actually, I'll color them nicely, that we see a heads on coin A, or see a tails on coin A, or see a heads on coin B or tails on coin B, etc. Right, and each one of these outcomes changes, has a different cost. Right, these heads have cost 0, and these tails have cost 1. C equals 1, C equals 0. And given our understanding of the probability of each of these things occurring, we can move our information about j backward in time to some initial state where we're trying to make a decision about which coin to pick. And that decision about which coin to pick will depend on both the payoff of that coin at that particular time and also what we expect to learn, how our knowledge state will change, and whether our knowledge state will leave us in a better position to make decisions in the future. So even though it's just a simple Markov problem, it encodes the learning problem within it, and it actually captures all the subtleties of learning and acquiring knowledge and exploration and exploitation within this standard Markovian partially observed framework. So, and of course the nice thing about it is the states, alpha, beta, are all just integers or half integers, depending on your prior. Here our prior is 1/2, so they're all going to be half integers. So you can solve this problem on a computer, and maybe I'll do a lecture on how I did that.